Going live, going live. Okay, we're live. Hello, world. My name is Alan. We're practicing LeetCode live. And for today, the problem is about graphs and about depth first search. Or actually, it's about breadth first search. Yeah. This is the third problem for today on this. I'm working but yeah, it's BFS. So B stands for breadth. Now that we clarified that, let's look at this problem. It's one of the first 1,000 problems. I mean, in the order number on LeetCode. It's a top interview 150 problem. So it should be kind of one of the classics. I hope it's sharing. It's the problem is 909 snakes and ladders. I like when there is some real life metaphors, some objects involved. I am not a fan of problems that take more than 10 pages to describe or that take like 24 lines. But let's see if we can understand it. Yeah, you're given an n by n integer matrix. That's a good beginning. I like that. I understand matrix and I understand n by n. Where the cells, and by the way, let's start the clock. Where the cells are labeled from cells. 1 to n squared, so it's like 1 to n squared. Is there like an or? Boostrophodon in a bus starting from the bottom left of the board and alternating direction each row. Okay, so it goes to 6 from left to right, and then from 7 to back from right to left. Boostrophodon, nice. I like that. I like when there is something special. Is a style of writing in which alternate lines of writing are reversed. Alternate. Wonderful. Wonderful. Okay, you start on square 1 of the board in each move, starting from the square current. Do the following. Okay, so far I understood that, okay, they go this snake path direction, snake like, and alternating direction, and it starts from this corner, and there is some things you can do. In each move you can do the following. Choose a destination, and I'm still not even at the half of the description. Okay. Choose a destination square next with a label in the range. Oh my goodness. Choose a destination square. Okay, I understand that. It's called next. Okay, you choose it with a label in the range. Okay, now I understand, because they're labeled. Okay, their values, they're actually, okay, they're labeled. That's the initial data in this matrix. Label in the range. In the range. By the way, before we go, I like to look at the constraints just to know what we're dealing with. Board length, okay, and board length, length. Okay, so it's list 2 by 2 and maximum 20 by 20. What is this? Is either -1 or in the range. Where is -1? I will see. Okay. Well, n square. That makes sense. Yeah. So it's like the maximum. Yeah, that's why n square. The squares labeled 1 and are not the starting points of any snake letter. Okay, we'll come to this again, but the thing is, so the next with the label in the range, current +1. I mean, I understand what current +1 is. So it's like if you're on 5, you can pick something that's at least 6. And the minute, okay, current +6. Why 6? Why? ¿Por qué? I don't know. Just because, just 6. The minimum of current +6 and n square. Okay. I'll believe you, because current +6 must be more than n square. N square could be just 4 or 1. But current +6, but you pick the minimum, so it's the lowest. So the minimum, if you are on 1, you can start with 2, and but minimum of is 1. Ew. Oh no, n +1, not the current square, n square, n square. So at least +6. Well, n square is always bigger than anything. Why? ¿Por qué? N square is always, it's not the current, it's the it's the n by n matrix. Why the minimum? Oh, because, well, current could be like at the end, so +6, got it. Yeah, so essentially, so within this, the maximum, but at least +6. So if you're on 1 +6, it's 7. So that will be between 2 and 7. So then square will kick in only if that +6 is higher than that. Otherwise, it's always gonna be between +2 inclusive and +1 and +6. The choice simulates the result of a standard 6-sided die roll. Oh. Okay, this is the die roll. That is, there are always at most 6 destinations, regardless of the size of the board. Okay, in each move, I get it. If next has a snake or ladder, if next has a snake or ladder, you must move to the destination of that snake or ladder. However, oh no, not however. Otherwise, you move to the next. The game ends where you reach the square n square. Squared. N squared, right? Is that the right? N squared. It's not n square, it's squared, right? Usually pronounced as n squared. Yeah, I just yesterday, or like literally, I discovered it's not n square, it's n squared. Because until then, I just said n square. Well, it's squared. Back to our problem. Okay, so just to recap, there are these snakes and ladders weird. I don't know how they come in the input data, where you find them, but they are there. But yeah, so you can choose the 6 possible steps, and among the choice, if you get on snake or ladder, you go to the end of the destination. The game ends at n squared. The board square on row R and column C has a snake or ladder. Okay. If board RC is not -1, the destination of that snake ladder is board RC. Squares 1 and are not the starting points of any snake or ladder. Oh my goodness. I should drink more mango juice. I want mango juice. I want mangoes. The destination of that as, or if board RC is not, if that or is, know that you only take a snake or ladder at most once per dice roll. If the destination to a snake or is the start of another snake letter, you do not follow the subsequent snake letter. For example, yeah, this looks like a problem that you need to look at the example, because yeah, sometimes the description is just super not human, not like inhumane, I should say, even sometimes. Something. For example, suppose the board is this. What is this? -1, 4, -1, 3, and on the first move, your destination are not the pointing square starting points of any, and is square 2. You follow the ladder to square 3, but do not follow the subsequent ladder to 4, to 4, to 4. Return the list number of dice rolls required to reach square ends. Squared, if it is not possible to reach, return -1. I'm starting to guess that, yeah. So they're not now labeled, they're not values. Okay, so the cells do not have values of this 1, 2, 3, 4. The cells by default have values -1, -1, but they're labeled with that order, snake order. That's their labels. Okay. In this primary example number 1, we have -1s almost everywhere except for a couple of places. So we have so they call them ladder if it moves you up, and they call them snake, I guess, if it moves you just. By the way, I don't know if the ladder always moves you only up. It might actually move you down as well. I don't know. Let's see. In the beginning, you start at square 1 at row 5, columns. Okay, yeah, 5 columns 0. Got it. You decide to move to square 2 and must take the ladder to square 15. Okay, by the way, you can only move to the bigger label. And then decide to move to square 17 and must take the snake to square 13. I see. So the snake worked backwards in this case. You then decide to move to square 14 and must take a ladder to square 35. By the way, you must, if you must move to the destination of that snake ladder. Okay, so 14 really like pushes you really high to 35. And you then decide to move to 36, ending the game. This is the lowest possible number of moves. High number, lower number, smallest. Yeah. To reach the last square, so return for board. Okay, another example is -1, -1, and then 3. Well, in this case, you start at 1, then you can just go right to the end. So 6 is enough for you. 6 is it's within this first move. I see. I want to look. So it's 20 minutes into where we are into, and we just read that the problem. I think I should work on my reading because I don't think it takes me 20 minutes to read one page. What is the average reading speed? Average reading speed, words per minute. I'm going on the material being read. Words per minute for nonfiction. Well, reading aloud typically is slower. Technical material is 50 to 75 words per minute, but I mean, this is obviously technical, but it shouldn't take 20 minutes. But I think when you're dealing with I think that part should be worked on. Okay. Anyways, one tricky thing I've noticed. What have you noticed so far? One thing I've noticed is if you hit a ladder or a snake, you can actually might actually drop back really far back. Yeah, you can like lose a lot of progress, but so they actually go backwards. But at the same time, sometimes it makes sense to take that backwards movement to actually jump on another ladder that will move you much further. Yes, so some shortcuts. So if there are shortcuts, you might want to use them. Yeah, and those ladders could be great shortcuts. Snakes. Why do they call them snakes? What is, I wonder, like this one on 13 is 17. Snake. Oh, by the way, it's one directional. There is no snake that starts at 13 and moves you to 17. So it's only from 17 you can drop back to 30. Yeah, you can fall back to 13. And with letters, I guess is the same thing. Yeah, so like this ladder can take you to 15. This ladder can take you to 35. The second one, and yeah, it's at 14, but it can drop you back. This one works like that. Why should we call it like a snake or a ladder? I don't know. Maybe because it's like letters are actually moving you forward, and snakes actually moving you backwards. Yeah, their destination. Maybe because look, it looks like that. So it's like this logical name. Because they could be like they could move you any point on the board. Shortcut. Okay, that in graph terms, that means there is a connection between this node and another connection. Yeah, a shorter connection between this node and that node in this direction. Otherwise, yeah, all the nodes, they are connected in one direction. You go in the order of increasing. In the increasing order. And yep, that's it. So you have this like 3. I'm just doing a little drawing, and you start with 1, then it's 6, 7, 12. So yeah, so it goes like that. There you go. But there are some shortcuts. There's a shortcut from 2 to 15. And from 14 to 35. Well, the graph usually, and there is a there is a snake, yeah, from 13 to 17, yeah, so 17 and 13. Yeah, so that is a snake. Otherwise, these are pretty good. And it's a ladder. Yeah, in the terms of graphs, this is just another edge. Essentially, we have a linked list with these labels. But some of the nodes, if you step on them, those nodes are they're shortcuts. Might be a forward shortcut like a ladder, or might be backward, a drawback like a snake. Now we have to start from 1 and add, and we must get to the n squared, to the last one, the highest label, and within as minimum list number of dice rolls required. Return the list number of dice rolls to reach the square. Wait a minute, why did they all of a sudden? I mean, in this example, you decide to move to 2. It's not like you roll the dice and then decide to move to square 17. So 1, 2, 3, 4. Less possible number of moves. Why is this like this dice? I don't know. It's just a confusing part of it, I guess. Just there is. Yes, I understand that this, but there is no random element in this. Dice meaning adds some uncertainty, but you all already, there is. It's not. That's not what they mean, I think. Although they do emphasize that it's the choice simulates the result of a standard. So choose a destination square next. The choice simulates the result of a standard 6-sided die roll. There are always at most 6 destinations, regardless of the size of the board. So, without the snakes and ladders, you would have to go like 6 plus 6 plus 6 till you get to the end. With snakes, you might not be able to do that because you need to avoid stepping on the snake, on the head of the snake. Might draw you back. Now, so as long as you go staying away from snakes, but with ladders, that's a next level of complexity, because now you want to use those shortcuts, those ladders, you can use to move even faster. And it could be so much faster that it actually makes sense to use a snake to move back behind the ladder and then use that ladder. Social ladder. 30 minutes into, we have this is like a recap of the problem statement. I wonder, but I mean, In terms of graphs, in terms of graphs, it looks like a combination of like, when we're talking about shortest paths, it's BFS. BFS allows you to, yeah, and we need to return what? The number of steps, okay, in the shortest path. Okay, the BFS, as you check out the neighbors and where they can take you and move with those neighbors. And once, yeah, you just check out all the neighbors. But we, in terms of possible moves, it's a choice of neighbors. It's a choice. Like generally you have, yeah, because you can move like within the next 6. That's the choice you have. This is the choice you have. Yeah, you can move within the next 6, so you gotta like build that. And can we just use a typical BFS? And yeah, that's probably the way to go. The way to go. We just, yeah, let's say we figured out this this alternating direction movement, and yeah, the actual neighbors are these next 6, yeah, or up to 6, yeah. They are the actual neighbors, because you can't move any other spot. So yeah, and so you look at this one is essentially 15. Now 15 will have also its own 6 neighbors, and one of their neighbors will be 13. Yeah, 13 will have its own 6 neighbors. One of them will be 14. And 14, well, 14 is actually 35, so it will be 35, so which will have its one, the result is one of their neighbors. That's breadth first search. Classical breadth first search with some hoops we need to jump about this alternating. I mean, I guess we could just create a linked list out of this. Let's create nodes. A linked list which will have It could be, yeah, it's a singly linked list we've only just begun to see. Yeah, we could organize it. Yeah, we could think it through, and well, in that case, we'll need to use this memory. In that case, yeah, we'll need to use the memory. But I mean, the traversal will be pretty simple. And we can record all that information into a linked list. You're right. Could we do the traversal on this matrix? How do you traverse, like starting here? You like once it's because let's say you go from here to 7. So after 6, so at every n, the direction changes. If we want to use the matrix as the initial information holder, then we need to, we need to be able to traverse that thing. Starting like this n minus 1, 0. Then we'll be like going 0 till n. And then once it hits n, if it's and n could be, it's the forward direction from 1. Yeah. So if you're like at 8, well, I mean, you will have to simulate that traversal anyways. So that's a subproblem. Just we need to know what is the next 6 for this specific number. Yeah, like for 1. What are not the labels, but what are their, like you choose, because initially, you will be increasing the column. You'll be C++, column ++. And at some point, you will decrease row. And then you'll start decreasing column. Then you'll start decreasing columns. So, but you'll have to do it anyways, right? All right. Even if we decide to build a linked list, we do need to traverse it in that fashion. Yeah, so it's probably a matter of like modulo to n is the change of direction, and And then we also, when the ladder shows us 15, we need to know, we need to start from 15 after that. Well, we could get to 15 in other ways, it doesn't matter. So what is, well, the labels are pretty simple. This change of, this is gonna be this alternation of direction. Yeah, when the label is is divisible by n, let's say that's a change. If it's even, like this is odd, so we're gonna start, we're gonna move up. We could I mean, explain these rules because it's actually pretty recognizable. I mean, what happens when you, what is your direction? What happens? Essentially, you add 1 to the column because you move on columns, okay? You change the row only when it's divisible. When it's divisible by n. Then you actually change the row, increase the row. So rows are like, but I mean, how do you know the label and what is the position of some value like 10 labels back? Like, I mean, it's easy to know the label, like, 7 minus 7, like 10 is 7. Where is 7 then? Okay, the matrix doesn't even have the 7, so you need to, what is 7 on the matrix? Why do we need to know that? We need to find the position on it. What if it's actually, so what is up, so 7, okay, wonderful, 7, but we need to know its coordinates so we can move, figure out the direction from that point. We know that 7 is like odd. If we divide it by n, it's odd. So that means we are on the second layer. Well, odd means it's just odd. That means a backwards direction. Okay. How many? We have 1, so that means it's like 7. Second, 1 plus 1 is just after 1. It's after 1, and then in the left direction we move this remainders. So you can use math to do that, or and like if any of those shortcuts like just fly you somewhere, then you can like locate yourself. We can locate ourselves on the matrix. Or we could also save the pointers. but we'll need a map then. There's like there's only 400 max, 400 squares on this thing. Yes, we can have a map of label to the square. Label to square map. Or just create a function. Get coordinates, like func get coordinates. It will take a label, for example, integer, and return slice of integers. Yeah, it's not a rocket science. I mean, it will fly you as a rocket, might fly you as a rocket, but it's not rocket science. Yeah, this function could solve that. So yeah, we can, if we go high level, well, then it's pretty simple then. Yeah, then we just do the we'll need a queue, which will be and by the way, so like we'll look at the 6 neighbors and we'll queue their neighbors, their 6 neighbors. Right? Right, yeah. We'll queue their 6 neighbors. Yeah, so queue is integers that has label 1 initially. And label 1 yeah. And then yeah, we count the moves. Will for queue length of queue more than 0. Yeah, we'll once we get a next row of neighbors, we can pretty much start working on it. Well, we need to count each 6 as a separate move. That's why we'll need for range 6, we know that. It could be less than 6 if it depends on where we are. If essentially, if we are at n, somewhere where we can move to n with 1 step, that's that's 1 move. Okay, so But in general, that's, yeah, there will be 6. Oh no. Oh no. The next, so we'll get 6. We have 6 neighbors here. Each of these neighbors, well, queue up. The problem is there is a huge overlap. So these 2 neighbors, well, maybe not this one, but these two have, pretty much everything is overlapping in their neighbors. Yeah, their neighbors are overlapping. So that's, then we need to figure out what we actually want to count. But one move is any of those 6. So that's our neighbor. Essentially, those are our neighbors. One of those 6. That's our choice. But like this one, this is actually not 2. This is 15. So the neighbors for 15 are definitely different than the neighbors for 3. So we might wanna. I don't know if we just blindly queue up whatever we have in one move. Okay, for this, we start with 1. Actually, yeah, we are initially in 1, right? Then, so initially we just 1 with 6 neighbors. Then we'll have a choice of 6 other options, 6 moves to 6 other positions, and those will queue up. Each will queue up 6 next ones. With the exception of this ladder, lots of overlap. There will be lots of overlap. Or this snake will actually move you back, so your the new neighbors will be these 6. So I'm trying to avoid those overlaps. Because if you just queue up what 3 gives you, well, we'll initially have 1, and we'll go okay, give me the neighbors of 1. We'll go through the 6 neighbors of 1. And we'll queue them up. But we will check for each of them. We will check, are you 1 step away from by the way, that's all we need. Are you 1 step away from or actually, once a neighbor is n squared, and we're done. We don't really need to do anything else, right? Should we track visited? We can color them like with -2, which will mean visited, so we don't go again into the same spot. Yeah, I guess we'll mark them. And by the way, that probably includes the snakes and the ladders. Yeah. So we'll in the matrix. Yeah. Yeah, in the matrix we'll visited with -1. I mean, once we actually process this 14, we don't have to go there again. Like once we actually queue it, well, we'll queue it, and when we queue it, once we okay, queue is this, so we'll say now our class. If I could only type now, is Q0, so queued, and let's now dequeue that thing. Q is, yeah. I need some power for my laptop. The streams are quite power consuming. So top, bottom. With -2, yeah, we'll mark them with -2. And that includes, I guess, the ladders and the snakes. It doesn't matter. Does it matter? Does it really? Because we don't want to loop around twice. We want to check some path only once. If we already checking out some path, it's visited. Yeah, so -2 is a good mark. So we have now get column row or coordinates or XY. They call them row and column, which is the shorter way. Get row column for this label for now. Yeah, we'll get us the row column. But we actually need to move to the next 6 times. Yes, so we need to say that, because for range 6, by the way, now we'll be yeah, so we have some, this is one of our moves. So as we step in here, we'll say moves plus plus. So this is our first move. And we're gonna go over now we are going to go over 6. By the way, size is length of queue. So for size, that's what we're gonna go over actually. Yeah. We need that queue different, that length different. Yeah. And that's the move actually. So we have something on the queue. We have one move at least. I think so. If that value is not n square. Wow, the machine even, my Mac Pro even turned on the fans. The video streaming is actually so CPU, or I don't know, there's something in that monitor resources, some resources consuming. It's probably energy. Yeah, it's probably this. Well, it's not the memories part. It's just it's obviously it's using a lot of CPU for some reason. I don't know. Maybe I wonder if on a different machine, maybe like my PC, it might not go that crazy. But, and by the way, this is like we're in the second hour already, and I think, I mean, the main idea is pretty is already like the high level solution is kind of already here. So the next step is to implement it. So we are going to go over the next 6 neighbors, queue them up, as long as we are within the n square. And by the way, we don't really need to square anything else if we are already one step away from, so we'll need to fix that. And it's kind of, we're pretty close. But it will take some detailed work on this traversal and all these things. So I want to give my machine a little rest, because and get back to it after a little break. So I think we figured out the logic, and we have some takeaways, like try to read things faster, read the description faster, not 30 minutes. And and go from top down. So well, I think that's it for this recording. I'll have some little break and continue and finish solving this problem. But that's it for this hour of the video. Thank you for watching, and we'll see you in the next video.